A big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast episode 64. In this podcast we cover topics such as engineering, AI, neuroscience, life, and other interesting topics and fascinating ideas to educate, inspire and engineer people's minds all around the world. I'm your host Yusuf, and for this episode of the podcast I'm very excited to welcome Dominique Madier to my show. Dominique is a senior aerospace consultant with more than 20 years experience and advanced expertise in finite element analysis of static and dynamic problems for linear and nonlinear structural behaviors. He has conducted detailed finite element analyses on aerospace, metallic and composite structures. He is the author of the FEA book Practical Finite Element Analysis for Mechanical Engineers, a book about the best practical methods on guidelines for the development and validation of finite element models. It gives to the structural engineers the keys to developing accurate and reliable finite element models. On top of his consulting work as a freelance engineer, he recently created FEA Academy to publish and promote his book and to teach finite element analysis online and on-site to students and engineers. In this podcast, we covered the difference between FEA and FEM, FEA concepts like nonlinearity and degrees of freedom, Dominique's book on FEA, the FEA Academy, most common mistakes in FEA, verification, validation and the future of FEA, and so much more. For updates on upcoming podcasts, projects and videos, make sure to follow me on Twitter as well as on Instagram. To join my weekly newsletter engineedmind.sh where I share exclusive content, visit yusuf.substack.com. And now, ladies and gentlemen, here's my podcast with Dominique Madier. Hey Dominique, welcome to the show. It's a pleasure to have you here.
Hi Yusuf.
Yeah, this is awesome. So finally we meet together, at least e-meet. And thank you for accepting the invitation to be on my show. It's really a pleasure. It's an honor. Thank you so much. Today we want to talk about FEA or FEM, how some people call it. But before we jump into that, a lot of people know you on LinkedIn to be an FEA expert. So I'm very honored to have an FEA expert on the show. Could you maybe give us like a 1 or 2 minute bio? Who is Dominique and where do you come from and what is your career path?
Okay, yeah. But first, I want to say thank you very much, Yusuf, for inviting me to your podcast. To me, it's a real honor because I am a huge fan of your podcast. And when I say that, not only the interviews you are doing with specialists on many domains, which are super cool, but also your MATLAB series and your CFD podcast. Very well done. To be honest, I love it.
Thank you so much. Very flattering.
No problem. So I'm Dominique Madier, and I'm a stress and simulation engineer in the aerospace industry for more than 23 years now. Yeah, 23 years. And my domain is solid mechanics and structural analysis for the sizing of aircraft and engines. Mm-hmm. And I started by performing stress analysis using what we call the conventional strength of material methods. But I did the move to FEA very soon during my career and to become a specialist in finite element analysis. So in 23 years, I've had the chance to be involved in many projects, some more motivating than the others in Europe first, and then in North America. So I started for Airbus, Dassault Aviation, and then when I came in North America for Bell Helicopter, Bombardier Aerospace, Pratt & Whitney, Canada, and their subcontractor for sure. And on regional jets, business jets, and commercial aircraft, okay? And also engines. Because it's part of the aerospace industry, not only flying machines, but also engines. Mm-hmm. So now I am a freelance engineer offering services in FEA from Montreal in Canada. And in parallel, I'm running the FEA Academy project. And the objective of this project is, and this activity now, is to teach FEA to students and engineers in solid mechanics and structural analysis. So it is what I'm doing now.
Yeah, that's excellent. You have plenty of knowledge, which I think you try to put in this thick book right here, which is, I have to say, Dominique, it's the best. I have some FEA books, but this is one of the best ones. It's my favorite one now. And I say that unbiased because when you go through the book, you basically cover everything. So, but we will talk about the book in a few minutes. What I want to know from you, Dominique, is of course you're an expert in FEA, but how would you first of all define FEA? I would sometimes ask experts how would they define their own field. Maybe you could define what is the finite element method and what's the difference between FEA and FEM.
Oh, that's a great question. Yeah, because sometimes it's confusing for people because both terms are used, FEA or FEM, and people don't realize what is it. So that's a great question. So let's start with the basic. FEA stands for Finite Element Analysis, okay? And FEM stands for Finite Element Method. So the FEM, it is the method we are using to conduct the FEA, okay? So I like to say that FEA, it is a discipline in which mathematics, engineering, and physics and computer science meet, okay? It is the conjunction between those four disciplines. So what we are doing with FEA, it's to predict the real world with the mathematical models, okay? So the objective is to define a design, to conduct an analysis in order to define a design without building a prototype. You know, few years ago, before that FEA was used intensively, the engineers were doing they were doing prototyping. So they were doing basic analysis most of the time and calculations. And to verify that the analysis, the calculations were good, they were building some prototypes and they did some tests on the prototypes. And then based on the results they obtained with the prototype, they were doing some modifications, they redid the analysis and so on. And they built another prototype and they continue like that. So they did a lot of prototypes before to arrive on the final product, okay? But it was time consuming and it cost a lot of money to develop a final product. And especially in aerospace, because to build a complete aircraft, to test it and repeat that a lot of times, they did it because a lot of aircraft flew that, using this method. But as I said, it took a lot of time, it cost a lot of money. So by doing FEA, Finite Element Analysis, this prototyping is now done at the virtually using a computer. And for that, we use a method named Finite Element Method. And this method, what is it? It is, we know that all the behavior in the world are described by the partial differential equations. Think about a behavior in the world, and it is described by partial differential equations. So if you solve the partial differential equations, which govern a given physics, you are able to do some predictions, okay? But the problem with this method is that a computer cannot solve directly a partial differential equation, okay? So in order to solve a partial differential equation, we use the finite element method. Why? Because the finite element method, based on what we call a discretization, permits to transform the partial differential equation into, or the partial differential, it's not necessarily one partial differential equation. It can be a system of PDEs, partial differential. So the FEM, the finite element method, permit to transform this PDE system into a matrix system. And the beauty of that is that the computer is able to compute the matrix system and to solve the solution and to give us to predict to help us predicting the behavior of the system. So it is what finite element analysis is, and is very powerful because it can be applied in many domains. It can be applied. Personally, I applied it on solid mechanics and structural problems, but it can be applied also for thermal problems, for acoustic problems, for fluid dynamics problem, a lot of problems. And we can, maybe we will talk about that later, we can create some interactions between those disciplines and in order to solve very, very complex problems. So it is what FEA is. And it is the difference between FEA and FEM. FEM, it is the method we use to conduct an FEA.
This is very well explained. Thank you so much, Dominique. What I would have as a question now is, of course, we have these matrix systems, which could be very, very tiny, where we have a look at one beam and kind of derive the basic equations with the stiffness matrix and so on. What is one of the biggest systems that you have seen? Of what order of magnitudes do we even talk about? Like, how big are these matrices? How many degrees of freedom do we have?
Okay, yeah, good point. Degrees of freedom. It is the key, the key term when we are speaking about the size of a FEA. Personally, the maximum I have computed, it is 10 million degrees of freedom for a local analysis, because typically in the aerospace industry, but also in other industries, we have different level of simulations. The first level, it is what we call the global FEM, which are global representation of a system. Okay, but with those global FEM, we don't represent the system in detail. We just want to capture global effect for the system. And after that, we have the detailed FEMs. The global FEM usually are 1-2 million degrees of freedom. Okay, but it's not enough sometimes, and most of the times it's not enough in order to capture very local effect or very complex effect or effects, or when we want to combine a lot of effects. You see what I mean? Yeah. So in that case, we are going into the detailed FEMs in order to capture more details. So in this case, we can reach 5 million degrees of freedom, and even between 8 and 10 millions. We can do that because the powerful of the computer is there. We don't need a quantic computer to compute 10 million degrees of freedom. With the technology we have now, what we call HPC, high performance computers, where we combine hundreds of CPUs in the same system, we are able to compute up to 10 million degrees of freedom. And now in 2021, but I'm pretty sure soon it will be much more than that. I'm pretty sure that we will compute 20 millions in the coming years. It's clear.
Very interesting. Yeah, also a personal question to you. Why did you even choose FEA in the first place? What's the intriguing idea for you? Why did you choose FEA? Why not CFD, for example?
But, okay, to me, FEA, CFD, FEA is applied to finite element analysis is applied in CFD. Okay, it's not the same method because in solid mechanics, we are using the finite element method, but I know that in CFD, they are more using the finite volume method, but it is an FEA. It is FEA at the end, okay? So you ask why, what is motivating to me with in doing simulation by FEA? As I said at the beginning of the interview, to me, FEA it is a discipline where mathematics, physics, engineering, and computer science meet. And personally, I have a strong interest in these four disciplines. It is why I am captivated by FEA. So, being able to do predictions with a mathematical model before a product has been built, influencing the design of this product to meet requirements, because for sure we have to meet the requirements, and then verify afterward that that it behaves like you predicted. It's something very satisfying, believe me. You know that because I'm pretty sure you have already conducted some FEA before me. So what also motivates me a lot to FEA is the fact that it is an evolving discipline. And it's applied in many domains. As I said, I applied on solid mechanics, but it's applied in many domains. Yeah. So when you work as an FEA analyst, you know that you will learn new things every day. Each analysis is different from the previous one. Okay, even though there are similarities between the analysis. each analysis has its own characteristics, and which the FEA analyst must adapt and face in order to solve a specific problem. So it is why it's always different. Okay. I like to say that doing FEA, I'll explain. It is something I present at the beginning of the book. To me, it's like playing chess. Personally, I love this game. I love playing chess. I play a lot with my kids, and conducting an FEA, it's exactly the same. You must anticipate the problems, predict behavior, and adapt your strategy. And just for that, it's really fun to do FEA. So all this makes simulation an extremely motivating field. So I can say that personally, I do FEA by passion. And you know this quote, Youssef, choose a job you love, and you will never have to work a single day in your life.
Yeah.
So it is what I am doing FEA.
Yeah, that's beautiful, Dominique. And I hope people who have not delved into FEA so far, and hopefully listening to this podcast, once we share it, they find love for FEA, for computational mechanics methods, to maybe apply their own FEA problems or solve their own FEA problems.
Yeah, you're right.
Also, you have a lot of love for this topic, which you have put into this thick book that I presented in the beginning. Could you explain what was the motivation for you to write this book in the first place, and who is it for? Who should get the book?
Yeah, okay. A lot of people are asking me this question, to be honest. Since I published the book, I received a lot of messages from people who are asking me that. So even though I have been involved in some amazing and interesting projects from the start of my career, I have to say that my learning process in FEA was a long series of frustrations based on trial and error. And just because of the poor quality of the literature concerning the practical aspect on FEA, okay, and I insist in that the practical aspect of FEA. When I started out in the aerospace industry in Europe first, the use of FEA 20 years ago, more than 20 years ago, the use of FEA was not very developed. So it was difficult to find mentor to rely on and to learn from. So as a result, I had to learn on my own by experiencing the concept one by one, step by step. Okay, so the process was rather tedious, I have to say, and challenging at first. But it also allowed me to understand FEA in depth. By following this process, this concept by one and step-by-step concept, so process, it allowed me to understand FEA in depth. So it is good also, you know. So while owning my knowledge of modeling techniques, I noticed that many engineers had learned FEA from a software point of view, and that they skipped the first stages, which consist of learning the basic theory first and the proper modeling techniques. And now I'm convinced that such an approach is problematic because some FEA analysts make incorrect assumptions, and more than that, they generate flawed analysis simply because they are unaware of the basic FEA rules. Do you see what I mean? Mm-hmm. So 20 years later, I made the decision to write the book that I would have liked to read when I started my career as an FEA engineer. Yeah. So I wanted to write a book, simply to write a book for all structural engineers wishing to solve complex problems using FEA. And when I say all structural engineers, I mean including both experienced engineers, but also students in mechanical engineering, in mechanical structural engineering. I wanted to write a book to assist with the FEA learning process and to help engineers avoid the similar sense of frustration I experimented, you see? Mm-hmm. So, as you know, there is much information in the published literature regarding FEM theory. You can find a lot, if you do a Google search right now about learning FEA, you will find a lot of references regarding FEM theory. But you will find little on practical FEA, what I call modeling techniques for mechanical engineers. So with this book, I want to fill this void by offering the best practical methods and guidelines available for the development and validation of finite element models. So based on my own experience as an FEA analyst, the book contains the methods I have experimented and perfected during my 20 years as a structural engineer. But I should say the methods I use every day and that I know that they good, very good result, that they are working, you see?
Yeah.
So this is the why I decided to write this book.
Very exciting. And of course, we will put the link to your book down in the description so everyone can have a look at it. It's available as an ebook, hardcover. What else do you have? Did I miss something?
No, yeah, it's hardcover and ebook. And for ebook, there is two options. There is the offline version, which is a license for two devices that you download on the device and you don't need to connect to internet. And for universities and companies, there is an online version, but it's from 10 users minimum and more. And you don't need to install any PDF reader. You read that online, but you need an internet connection.
Very cool. Okay. Makes sense. I'll put the link, as I said, down in the description. Everyone should get it. I have the book. I have to say, it's really the best book I've ever read on FEA.
Thank you.
Talking about the FEA Academy, of course, you have this great FEA Academy, and there are some plans for the FEA Academy. Of course, you would like to put some courses on the FEA Academy, if I'm not mistaken. Maybe you could go a little bit into depth. Why courses? Why is it better than a book? Maybe worse than a book? Maybe you can go in a little bit into depth here.
Yeah. If you wish, I can speak about the FEA Academy project in general. So yeah, my greatest interest from now, I think you understood that, is in helping the FEA community learning FEA. So for that, I created the FEA Academy project. And I'm already helping many students and many engineers to learn and better understand FEA. Thanks to internet, it's very easy to do that all over the world and to reach a lot. You know that better than me, to reach a lot of people all over the world. And by discussing with many people, many students, but also many engineers who are already using FEA, I realized that as professional in the FEA field, we could help university to teach FEA better. I mean, to teach FEA more from a practical point of view. Practical for me is a really important concept, you know. For sure, we have to say that universities are teaching very well the basics of the FEA theory to their students. But many students are telling me that they have no idea how to apply FEA for solving a real problem of solid mechanics or a structural problem.
That's right.
So it is really a problem.
Yeah.
Because students are looking for robust methods and guidelines that they can use to solve real problem day to day. So it is what I want to offer with the FEA Academy. First, by proposing the book, but also, as you said, to propose also courses and to propose mentoring about the practical aspect of finite element analysis for structural engineers. So what is really the FEA Academy project? First, it is a publishing company I created to self-publish my book, because I self-published my book because I wanted to retain my copyright. So I had no choice if I wanted to retain this copyright to self-publish my book. So first, it is a publishing company. And I use the website to promote and sell the book, as you said, in hard copy version and ebook format. But the website also proposes the replays for all the free webinars I am conducting on various FEA topics. And the replays are generally available 3 hours after the live sessions. The live sessions I am conducting on my webinar platform. So each webinar duration is between 30 minutes and 1 hour and a half, and cover a lot of various FEA topics. And the replays are usually, the webinars are usually announced on LinkedIn, and people can register on the FEA Academy website for free. And for this FEA Academy project, I am currently working on online courses And the first sessions, it's really new information. I'm giving now just the first time on this podcast. It will be available. The first session will be made available this fall. So it's a prime information, and the courses will be based for sure on the content of the book, but later more than the content of the book. Okay, it will. I will put more and more contents on those courses later. So to start with these courses, my plan is to offer 2 bundles. The first bundle, it is a 6 sessions course about basic FEA, covering basic theory. And it's important, basic theory, because I don't want to cover, we are engineers, okay? We are solving real problems. So we don't need to know all the details of the FEM theory. We just need to know the basic theory, okay? How a stiffness matrix is computed, how an element stiffness matrix is computed, how the global stiffness matrix is assembled, and how the solver compute the system. It's enough to understand what the solver is doing. So it is just that. And also the course will cover the fundamental modeling techniques for linear static, linear buckling, and model analysis. Okay, so it will be in 6 sessions, and it will be based on the content of the book. The second bundle, it will be a 4 sessions course about nonlinear analysis. Mm-hmm. So stay tuned on LinkedIn, because soon I am going to announce the opening of the first session, and the course is for me, it's very obvious to do the course because I already did those sessions for some companies, but now it will be conducted under the FEA Academy banner. Okay. And with the FEA Academy project, I'm also giving some online lectures about FEA for sure, for universities and companies on various FEA. So you can contact me in order to ask for a specific lecture on specific FEA topic. And I want to add that with the online courses, I'm going to launch also a mentoring service to assist students and engineers in their FEA learning process with one-on-one Zoom sessions. So I have to clarify how I'm going to conduct that, but it will be offered soon. So feel free to visit the FEA Academy website. There are a lot on the website, and I invite everyone to send me comments, suggestions, ideas, which could help the FEA Academy community. And if I can provide the services, for sure, I will provide the service.
Awesome. And this is great.
Yeah, no problem. Not that if you are interested in detail with the FEA Academy project, you can subscribe for free, for sure, to the newsletter to receive the news about what the community, what the FEA Academy project is doing. Don't worry, I don't send dozens of emails per week. Okay, usually the newsletter are sent only when significant events occur, like webinars or new services. Okay.
Mm-hmm. Yeah, cool. Maybe even in the future, once 2 courses have launched, I can make like kind of a review of your courses and see if it's really what you offer in the courses, if it's worth taking kind of a...
Yeah, for sure.
That would be
but
awesome.
Very soon, I will open a section in the website with a detailed description of the contents of the course. So you will see in detail what will be covered by the courses. And for sure, initially, I'm going to post only 2 courses, but I have a lot of ideas in my mind, and so it will be embellished in the future.
Mm-hmm. Great. Regarding your career, Dominique, I want to talk about the bottlenecks that you have come across. So, of course, you said you put a lot of knowledge in your book of bottlenecks that you have come across. Maybe give us like the top 3 or top 5 mistakes beginners make on their FEA journey. What would you say? Top 5 maybe mistakes? If it's possible, you can even give like a top 10.
Now, there are a lot of errors you can do when you do FEA. For sure, the first one Well, I don't like to say the first one because not everyone is doing the same mistake.
Yeah.
You know that. I'm pretty sure that I did mistakes that you didn't do, and reverse, you did mistakes that I didn't do. But for sure, they are typical. One of the first one is to do FEA without knowing the library of elements of the FEA package we are using. We know that there are generalities about a library of elements, but there are also specific topics about the library of elements. So the first thing is not knowing the library of elements of the FEA package we are using. And not knowing the library of elements, it means that we are not able to pick the right element, because when we do an FEA analysis, we have to select the type of element. Do we go with 1D element? Do we go with 2D? And even when we go with 2D, what kind of element we use? Even when we go with 3D, what kind of element we are going to use? So it is the first error that people are doing, not knowing the library of elements of the FEA package they are using. And after that, even knowing the library of elements, another typical error is not selecting the right topology of element. Sometimes people are going immediately with 3D elements where it's not necessarily needed, because it's you have to pay a computing time, a computing cost, when you go with the 3D elements. While you can go 2D, you will have the same result, but with a less degrees of freedom, so a less computing cost. Okay, but sometimes also selecting the 3D elements where the response of the simulation is wrong by doing a 3D analysis, while it's correct by doing a 2D analysis. And why people are doing that it's because it's very easy to mesh a 3D part most of the time. Using TET element, using TET nonlinear elements, TET 10, what we call the TET 10 elements. It's very easy to conduct the mesh. While conducting a 2D mesh requires more preparation. You need to extract mid-surface. You need to do a cleanup of the geometry in order to be able to do a 2D mesh. And sometimes people they don't do that. So they don't want to go with 2D mesh due to that, or because it takes time to do that, and they have pressure from the boss, and so they go 3D. But you know what? Sometimes they go 3D for a thin wall structure. But we know that the 3D mesh using TET 10 elements doesn't work with a thin wall structure. So it is typical errors that people are doing at first. Another error is going linear instead of going non-linear. And when I say that, not all problems have to be solved using non-linear solution. And more than that, first you have to solve the problem linearly before to go linear. Okay, because debugging your problem, validate your problem with a non-linear solution doesn't make sense. Okay, yeah. Validating your FEM, it's a linear problem, not non-linear. But sometimes you have your system behave non-linear because the reality is not linear. Most of the time, the reality is non-linear. And it is a mistake that some people are doing. They go linear instead of going non-linear, but in reality, they are faced with a material nonlinearity or a geometric nonlinearity, which have a huge influence on the results, and they ignore that. Okay, so it is one error. But going non-linear instead of going linear, it can be an error also, because maybe that your system has no linear behavior. So what you should go non-linear? It's a mistake to do that, because going nonlinear, you have to pay for that. You have to pay consuming time computing, and you have to pay for using specific modeling techniques which are very which have a cost in terms of computing time. Okay, so it's another error that people are doing. Another error is not covering the full range of analysis. Because when you do finite element analysis, you can do static, you can do buckling, you can do model, you can do dynamic, you can do nonlinear static. And sometimes in order to validate your structure, you absolutely need to cover, let's say, at least the static aspect, linear and nonlinear, but also the buckling aspect. Okay, and if you run a static solution, you will have a static answer, but the solver will not give you an answer about the stability of your system. Okay, so it is another error that analysts are doing. They don't cover the full spectrum of analysis. Sometimes because they are not aware about the full capabilities of the FEA package they are using. You see what I mean?
Yeah.
Because our FEA packages have a wide range of capabilities, and it's different. It can be different between different packages. Some packages have exactly the same range of capabilities, but some packages are good only are developed only for one or two capabilities, not for several capabilities. So, okay, I could say we can find a lot of other errors, typical errors, and I covered that in the book.
Yeah.
That people are doing in FEA, but it is what it is. So in order to avoid those errors, the best thing is to have a good practice a lot, and learn FEA from a modeling technique point of view. Don't learn FEA from a software point of view. Okay, it is the key in order to avoid the typical errors in using a finite element analysis, because it's very easy to do the errors, and the problem is very easy also to not realize that we did the errors. Okay, it is why when we do a finite element analysis, we have to do the validation process, the verification and validation process. And a lot of engineers are skipping this process. But it's a very powerful process because it permits you to catch the errors and to focus on the problems that your simulation has. So don't skip this process. It's time consuming, but it's very powerful. And again, I like in my courses to focus on this process, because it permits to find the mistakes, the errors we are doing in FEA, because everyone is doing errors. It's normal. And it's normal because we are using FEA to solve complex problems. If the problem is simple, we don't use FEA. We simply do n calculation and we solve the problem with what we call the classical method. Okay, but if we face a complex problem, for sure we need FEA. FEA is very good to solve the complex problem, and more than that, only FEA can solve complex problem, because n calculation cannot solve complex problem. So when we have a complex problem, for sure, it is clear that we can do errors because it's complex.
Mm-hmm. Yeah, I have two more questions for you, Dominique, before we jump to the LinkedIn questions, and then we have the famous podcast question rampage, where I will ask you 10 questions about you personally. The first question would be for you. You talked about verification and validation. Could you please give like a brief summary with respect to FEA? What is verification and what is validation?
Yeah, that's a great question, Youssef, because first, a lot of people are asking that, and a lot of people are confusing verification and validation. Okay, so the objective of the verification is to check the FEM and the FEA from a mathematical point of view. and the verification, also called the validation, also called correlation. It is to verify against test. Okay, so verification. Usually there are two parts in the verification. In the verification, first we check at the accuracy of the FEM, and we check that the FEM represent physically the system, the real system. Yep. Okay, from a geometrical point of view, that the FEM represent the geometry. We put the correct materials. We selected the right elements, and that the topology and the quality of the elements are correct. By elements, I mean the elements we are using for the discretization, for the meshing, that the boundary conditions are representative against the reality, stuff like that. This is the accuracy check. After that, after the accuracy check, we are doing what we call the mathematical checks. So there are typically 4 checks we are doing, and we have to conduct on the model by running the model in using specific conditions. Okay, and those specific conditions permit us to capture most of the errors in the model. Okay, and this is a very, very powerful method, what we call the mathematical check, because it's amazing how we can capture the modeling errors we are doing by building the FEM. So those checks have nothing to do with the real load cases we are going to run after. We are going to run in order to predict the behavior of the real problem. They are really mathematical load cases, but they permit us to check at the potential errors. And believe me, when the system is very simple, when it's only one part, most of the time we don't need to run that. But when we have a complex problem with a lot of components connected together to model a complex system, definitively this approach, this method will permit you to capture your errors. And believe me, you will do errors. You will miss a connection somewhere. Obviously, when you have a complex system, or you will miss a material somewhere, or you will forget a material somewhere because you have plenty of parts. There are a lot of reasons to do errors. And this method, this verification, this validation process will permit you to catch those errors. And after that, there is the what you call brilliantly the validation process, what we call also the correlation process. And this process is based on comparing the response of your system with a test. Okay. So usually what we are doing, and we love that in the aerospace industry, and more than that, it's mandatory. In order to certify an aerospace product, we have to do it. So what we do, we instrument the aircraft or a component of the aircraft. It can be only a wing, it can be only the fuselage, or it can be only the engine, a part of the aircraft. But believe me, the aircraft manufacturers, they are doing that on complete aircraft. We call that CAST, the static analysis. It is a specimen which represents the complete system. And we can do static tests with that, but we can do also fatigue tests. So we instrument a component or a complete aircraft or a complete engine with what we call strain gauges. And we apply some typical cases representing the reality, how the structure, how the engine will be loaded during its life. Okay, and we record the strains for many conditions, and we compare that with. We apply exactly the same conditions to the finite element models, and then we compare that with the reality, and we verify that the FEA gives the right answer, and it permits to do some calibrations and to adjust the finite element model in order to match the reality. But when we follow the previous step, which consists on doing the verification, the verification, and if we have followed the right modeling techniques, most of the time we are able to match very, very well the test. If not, we adjust the test for those specific cases, and we adjust the simulation. Sorry, we adjust the FEM to match the test. And the beauty of that is what? It's that we don't need after that to run the test for all the configurations, because for all the load cases, because in aerospace we like to run a lot of configuration, thousands and thousands of configurations, but we don't run those thousands of configurations with the test. But since we know that for some representative load cases, we know that the FEM is correct, is validated, then we can do all the modifications we want, all the evolutions, all the improvements we want, following the same modeling techniques, just using the FEM. So our prototyping is now fully virtual. You see what I mean? We don't need to build another prototype. Sure. So we will build the final product that we will deliver to the customers, to the companies, just using the simulation. So it is what is validation, verification and validation, and it is what is the powerful of this validation.
Yeah, very well explained, Dominique. I like it. Thank you so much. The last question we have for the main part of this podcast before we jump to the questions is, where do you see FEA going into the future? Where do you hope to see FEA go?
Oh yeah, to me, I see a very great future for FEA, a very good future for FEA, and I'm sure I'm right, because in 20 years I have seen the evolution of FEA, and it's amazing how FEA has evolved in 20 years. Yes, and we can see that there are many axes of development in simulation, which give FEA, but simulation in general. I want to speak about simulation in general, which give simulation a status of cutting edge technology. I have this term, cutting edge technology. First, there is the multi-physics simulation. Because multi-physics simulation permits engineers in many domains to solve problems where various physics fields are involved. I spoke about that at the beginning of the interview, that we mix different physics. We mix solid mechanics, we mix fluid dynamics, we mix thermal effects, we mix acoustic with the structure. You see a lot of physics. You understand what I am talking about. So the various physics fields are involved and they interact. And they can be considered together now at the simulation level to achieve more accurate engineering predictions. So this is the first axis that multi-physics simulation in which FEA is involved. Secondly, there is a technology I love, which is at the top now, but it's the beginning. It's not at the production level, but it is meshless technology. I'm pretty sure you heard about that. And the recent developments carried out by the simulation software companies around this technology, the meshless technology. And more particularly, there is one technology I follow, one meshless technology I follow. It is known as the, element-free Galerkin method. Yeah. And this method seems really promising. And to me, considering the great players who are developing things around this approach, I strongly believe that something great will emerge soon, because every software simulation software company are involved in that. It is not the only meshless technology, the EFG methods, which is where there are researchers, but it is, I think, one method which will give products, which is something we will use soon in our FEA packages. Mm-hmm. And to conclude on this topic, on another axis of development, it is the digital twin concept.
Yeah.
Again, around that, we know that there are a lot of discussions or a lot of developments around this digital twin concept, because this concept places simulation at the heart of a virtual representation of the product that serves at the real-time digital counterpart of a physical object or process. And this is, I think, this is the key to we want to live in a real-time world. Okay, the world is now real-time, and the digital twin concept will offer these capabilities to the development and to the monitoring of what happened to the product in the real life. So the evolving nature of simulations mean that these lines of development are making simulation more and more important for the development of the new product in order to improve their performance, because all of that has one objective, is to improve the performance of the product. And I would add that today it's impossible to think about developing a new product without the help of simulation and without the help of those new technologies. And to conclude on this subject, it's clear to me that artificial intelligence, and I'm pretty sure you agree with me because you are an artificial intelligence guy. So artificial intelligence with what we call data-driven models and machine learning, they are the last advanced technologies which will shape the future of the simulation processes.
Yep. Yeah.
So it is how I see the future of FEA, how the future of simulation. So it's very exciting. There are a lot of things to learn, to explore, to adapt, and to plug in our current simulations. You see what I mean?
Yeah. The opportunities are big, Dominique. I fully agree. And also, when I think back, I think we are kind of a bit spoiled, especially my generation, because we had powerful. When I think back, when I was in uni, I had actually a powerful machine. But the guys back then doing FEA, they had like the punch cards. If you imagine, like, and doing FEA back with punch card, that was funny.
Yeah. I worked with a guy when I started my career in FEA who worked with those punch cards, and he told me, you know what, Dominique, when I started, we had those punch cards, and we ran maximum 3 load cases, okay? Yeah. Because to run one case, we had to spend one complete day to punch the cards in the machine, okay? And after one day, we have only considered only one load case. But after one day, we didn't have the results. We had to wait for 1 month before to obtain the results. And it was a pile of paper like that. It was not visual. It was not graphical. It was only numbers, you know, and they had to crunch by hand the numbers. So yeah, we are lucky because now we have amazing interfaces. We have a very powerful computers, and we can run 1,000 of cases in a very short of time, and it will improve. Yeah. It will improve. Yeah. It is amazing because thanks to artificial intelligence and machine learning, for sure it will improve. So imagine what we are going to do in few years, even in few months, because it's evolving so fast that I'm pretty sure that at the end of the years of this year, it will have improved.
Yeah, 100%. So that was the main part of the podcast, Dominique. We have 2 LinkedIn questions. So the first one from Stefan Evans. I hope I didn't butcher his name. He asks, what is the best FEA software out there?
I like that guy. I know very well Stefan. and we have a lot of fun together. He is sometimes my guest on my webcast, and he has been a guest on a previous webcast, and he's the guest for the next webcast I'm doing about modeling voltage joint, the 18th of June, I think. So my favorite, you know me, I am an aerospace guy, so I am a huge user of the MSc products. So I'm using a lot Nastran, all the Nastran solutions, because it's a standard in the aerospace industry. And why? Because it has been used a lot, and there is a huge legacy on the aerospace, in the development of aerospace product with Nastran, and there are a lot of corrections which have been done, and we know that Nastran is doing very good results in a large range of situations. Static, dynamic, buckling model, linear, nonlinear, a lot of situations. So it is why it is used a lot in the aerospace industry. Yeah. So I am a huge user of Nastran, which is my favorite software. This is from a solver point of view, but from pre-post processor point of view, I am also a user, Patran user, an hypermesh user, and now I'm a new Apex user, which is the new platform that MSc Software released in order to conduct Nastran analysis. And Stefan Evans is the best teacher about this platform, MSc Apex, and I took his course, about MSc Apex, and I strongly recommend the Stefan Evans course, because it's an amazing course. And with his course, you will be able to use MSc Apex very, very, very easily. So yeah, that's my day-to-day tools: Nastran, Patran, Hypermesh, and now MSc Apex. So yeah, I can say that they are the best because it is what I use, but a lot of other products are very good in the FEA world. You know, Abacus is very good. NSYS is very good. ComSol is very good. A lot of FEA packages available on the market. I cannot name all of them, but are very good. You know.
Yeah. Excellent. Thank you for the answer. And Stefan Evans, if you listen to this podcast, you're invited to participate in the show. So yeah, that's that. Second question from LinkedIn before we jump to the question rampage and wrap the podcast up is, how did you simplify a complex topic like FEA and put it into a book? What was your key strategy behind all of this? Asks Ashish Srivastava from LinkedIn.
Okay. Yeah. It's not easy to simplify FEA because, as I said at the beginning of the interview, FEA is complex by nature. We use an FEA to solve complex problems. But while I was working as a freelance structural engineer, I had the opportunity to teach what I learned in FEA since the beginning of my career. I teach that to young engineers, trainees, stuff like that. And one of the most frequent questions I am asked is how to learn FEA. Okay, they learn FEA. They believe they learn FEA at school, but when they arrive in the industry, they realize that they don't know FEA, and they have to learn what is FEA from a practical point of view. Okay, in reality, to solve a real problem. Okay, so I realized that just like me, in fact, beginners are looking for references about practical FEA in the literature, but they could not find them. So I collected their questions, the questions from these young engineers, trainees, and together with the notebooks I had kept through my past experiences, I used them to build my table of contents. So it was easy for me to know what I am going to put in that table of contents, because it was based on what I learned, how I learned, and what are the questions from people who want to learn FEA. So in July 2016, while I was an FEA freelancer in the aerospace industry, I started to write the manuscript in my free time, because I was very busy by doing FEA for my customer. But in my free time, I did that by following a roadmap defined by my own notebooks and the questions that I have heard from the students I train in FEA. Yeah. So this is why the first word of this book title is practical. Yeah. Okay, because it is an answer to the questions first I ask myself when I learn FEA, but also an answer. The book is an answer to questions that students ask me. So it is how I managed to simplify the complex FEA world. But in reality, when you read the book, you realize that it's not simple to learn FEA. You have to invest a lot of time. You have to practice a lot. 3 recommendations if you want to learn FEA: practice, practice, and practice.
That's good.
If you don't practice, you will never learn FEA. Yeah. Because you have to make the mistakes. You have to understand why you make the mistakes in order to associate modeling techniques with this problem you need to solve, and in order to be able to use it later, or to use a variation of this modeling technique later on another problem, and so on. So practice, practice, and practice.
Yeah, got it. Very beautifully answered, Dominic. With that being said, we jump to the question rampage now. I have 10 questions for you prepared, some personal ones. Optimally, you answer them in 1 sentence, and then we move to the next question. You ready?
1 sentence.
If possible. Okay. First question is, what are you most proud of?
I would say there is a program I worked on. It is the C-Series program, because it was a blank sheet program, and we designed an aircraft from scratch, and it was a real success.
That's amazing. Question number 2, what's your favorite music genre?
Oh, it's jazz. I play trumpet, so I have a classic. My basic course was classic, but I jumped to jazz, so it is jazz.
Okay, nice. Question number 3, what's your best tip to work on a hard task productively?
Don't jump on the task immediately. Plan the job. Define a strategy. It is my recommendation.
Perfect. If you could spend 1 day with a celebrity, who would it be?
Elon Musk, definitively.
Cool. I would say the same. This is cool.
I know.
Elon Musk, or maybe Richard Feynman, or some other people.
I love Richard Feynman because I'm a huge fan of quantum physics. Yeah. I studied quantum physics before to study aerospace, and I love that guy.
Very cool. Nice. Love it. What's your most favorite chapter of your own book? What did you enjoy the most? Writing or like reading it yourself?
Writing, definitively, it is the chapter 21 about nonlinear analysis, because it's a complex one, and it's a concept which is not very easy to explain. But I receive a lot of good comments of the chapter, and I love this part of FEA, nonlinear analysis, and it is the one I prefer.
Awesome, great. What is your most favorite programming language, Dominic?
I love C, because it is one of my first language, one of the first language I learned. And now I would say also Python. I love Python. For sure, when you know C, learn Python is very easy. Yeah. But I learn and I love Python also because it's plugged on many products. It's available on many products, And it is why I love Python also.
Perfect. What's your favorite movie?
I have a lot, but I have to pick only one. Okay, I'm going to say Interstellar.
That's a good one. I thought you would say Matrix because it would fit FEA, but whatever.
I love that one also. Obviously.
But
that's good.
That's good. Yeah. Who's your favorite scientist? Could be alive or could be dead. Favorite scientist of all time.
Favorite scientist of all time? Albert Einstein. And you know what? Because that guy, just with a theory or two theories, he did a lot of predictions without doing any experiment.
Yeah.
And we are still verifying those predictions. This guy is always correct, you know.
Yeah, it's
so
crazy.
yeah, definitively Albert Einstein. Albert Einstein. Yeah.
Beautiful answer. Yeah, I love it. Question number 9: one superpower you would like to have.
Which superpower?
If you could have one superpower, Dominique, what would it be?
To travel in time.
Oh, okay, cool.
To travel in time, and just to visit old scientists like Leonardo da Vinci,
Nice.
Isaac Newton, guys like that.
Yeah, that's incredible. I like the answer. Last question for the question room page. It's a bit a philosophical one, maybe also a weird one. If you could choose to be a finite element, what type of element would you be and why?
It will be a beam. A beam because it is the most versatile element.
Wow,
you know?
That's beautiful.
So obviously, it's a beam. It will be good also for me to be a slim guy.
That's nice. I like the answer. That's good. That's good. Also philosophical one. I love it. Dominique, to wrap this up, maybe last motivating words for people who would like to delve into FEA or are currently doing FEA and would like some motivation from an FEA master like you. What would you tell them?
I would tell them a reminder. Remind that learning FEA, it's a marathon. It's not a sprint. It takes time to learn FEA. Just that. And no, also anything else. Sorry. Don't learn FEA from a software point of view. Learn FEA by learning the proper modeling techniques and the basic theory. And after that, learn the software. That's it.
Beautiful. I think with that, we can end the podcast. And I hope there will be a second part maybe in the future. Let's see.
Oh, yes.
And I wish you all the best, Dominique, for the FEA Academy, for your courses. And hopefully I can review some of them in the future and tell people, hey, this is an FEA expert. Take Dominique's courses. And as I mentioned, practical finite element analysis from Dominique Madier. I'll put the link down in the description. With that being said, thank you so much. And I wish you an awesome weekend. And we'll see each other on LinkedIn, I guess.
Oh, for sure. Anytime.
Thank you so much.
Thank you very much. Bye-bye.
Bye-bye.